So there are a lot of channels on YouTube that do coding analysis of games made by game devs and analyzing these games from that perspective. And I think those analyses are fascinating. I watch a lot of them. There's a lot of stuff about Duke Nukem. I think all that stuff's pretty rad. But I'm not a game dev, and I'm not so much trying to dip my toes in unfamiliar waters. I'm an end user guy. Okay, I take a game, I take the hardware, I put it all together, and I make it all work, and I make it all work better than ever toward providing the ultimate end user experience. That is my job. My job is not a coder, game dev, but these worlds do collide. And how they collided for me was I tested Ashes of the Singularity. I tested it thinking, oh, it's a CPU demanding game. I'm testing a CPU. This is for the 9800X3D testing. And then when I got into actually testing a game, I just discovered so much more. The story was bigger than what I thought it was. I learned about this game. I learned what exactly a game engine bottleneck is. And I learned about the Nitrous Engine and the people who developed it, which I found endlessly fascinating. And then that taught me a lot about why it was developed and the history of RTS games, which taught me a lot about the history of gaming. And I think the Nitrous Engine was came along at a critical moment in the history of gaming. And then I think the final lesson was about just making things work, which can be very, very difficult, which is where these worlds collide, and I start talking about the development of a game engine when I'm really just an end user guy, because you gotta make things work. Ultimately, you just have to make it work somehow, and sometimes it can be a challenge to make older games work on newer hardware. So we'll get into that as well. And I hope that you see this video as a tribute to the remarkable work of a few very special individuals. And I just wanted to make this video to show my appreciation. So this is my exploration of Ashes of the Singularity and the Nitrous Engine. Ashes of the Singularity was released in 2016. It was one of the first real-world showcases of the DirectX 12 API and of AMD's Mantle API, which was kind of the proto-Vulkan. It became the foundation for the Vulkan API. And it was truly designed with the future in mind. It was optimized for the quad-core standard of the time, but it was optimized in ideal circumstances for 8-core CPUs, which they were just really starting to hit the market. At the time, that might have been 6900K or maybe AMD's FX 8350, and maybe had a GTX 1080, or maybe you had two of them in SLI. And adjusted for inflation, that rig would have cost you about $3,200 in today's money. And that is the system that this game was made for. It cannot be understated how revolutionary this game engine was. And so we're going to pay homage. What follows is my experience getting this game to work on today's top-of-the-line hardware. Brad Wardell, CEO of Stardock/Oxide Games, referred at the time of the release of Ashes of the Singularity to 4 major generations of game technology. And in his formulation, the first gen would be DOS games, and the second gen, Windows games with sprites, and the third gen, Windows 32-bit games with 3D graphics, and the fourth gen would be 64-bit games with multi-core CPUs in multi-GPU setups. Now that was in 2016. So if we accept his premise, we might theorize a 5th and a 6th generation. Maybe the 5th one consists of real-time ray tracing and machine learning and super sampling. And perhaps a 6th and future generation would consist of cloud integrated simulation, let's say, like sort of along the lines of how Microsoft Flight Sim uses Bing map data, something like that, where you're playing a global simulation. And maybe we'll get to the point where AI is generating game mechanics on the fly. So the point is to go through this exercise of thinking what the future of games can be. That more or less puts you in the mindset of the creators of this game in 2016. It's not a stretch to think of Ashes of the Singularity as a game that was created to answer the question, what could gaming become? More specifically, what could an RTS game become? Wardell further states, imagine having to write an AI to handle a worldwide economy, fight a multi-front war, and plot an airstrike all in less than 20 milliseconds of CPU time. He mentions three principal constraints of video games: CPU processing, graphics capability, and memory. And in 2016, described a decade-long limbo in which those limitations had not significantly changed. Not to mention that DirectX 10 required Windows Vista, so until Vista reached a critical mass, if you played Ashes of the Singularity, you know about critical mass. Until Vista reached a critical mass, they were stuck on DirectX 90C. So Ashes was very ambitious. It was designed in part to counteract a decade of stagnation in the space. Wardell describes the days of DOS RTS games like Dune 2 and Powermonger, when being able to select a few units and move them across the map was an evolution in gameplay. But these games were limited to 320 by 200, 2D sprites, and 640 kilobytes of memory, which is about 15 times less RAM than what Notepad requires today. Then in the late 90s, we moved to 32-bit, a huge leap forward. Games could use megabytes of memory and render at 640 by 480 with 256 colors. Now, the AI of the day could only make decisions within the span of a single rendered frame. But you didn't care about that if you had a nice 14 kilobit modem. Then you could actually play against real people on the internet. And RTS games exploded. We're talking about this one, Total Annihilation, Age of Empires, StarCraft, Dark Reign. All these games were like Battlefield 6 is today. Then we moved on to discrete graphics cards. Offloading to the video card allowed for more nuanced camera design and eventually 3D units looking better than sprites. This is Supreme Commander. But all this came at a severe memory penalty. This is a relevant period for us to reflect on. You think memory is scarce now? Back then, the bottleneck was the manufacturing process. Yields were extremely low, and with the advent of personal computing, demand was extremely high, and the price-fixing conspiracy didn't help anything either. By the way, that also of relevance today, Micron was the company that ratted on everyone. Yes, they cooperated with authorities, and a bunch of executives from all the other companies involved in the conspiracy went to jail. And for all these reasons, 32-bit Windows had to do a lot with a little. It used a 4 gigabyte virtual address space, allocating 2 gigabytes for kernel operations and 2 gigabytes for applications. That was big for the time, but very soon started to feel restrictive. Memory limitations stalled what had been a meteoric leap in gaming tech. That 2 gigabyte memory restriction was the common system requirement all the way into 2015. Wardell really puts a fine point on it here. He says the hardware requirements for a strategy game were radically different from 2000 to 2004, but are nearly identical for strategy games released from 2006 to 2014. That's nearly a decade of 32-bit, 2 gigahertz processors, 2 gigabyte memory, and DirectX 90C. So other game genres advanced during this period, but RTS titles need to keep far more in memory than just what the player sees in front of them. And so this decade of stagnation in RTS games was a product not of a lack of creativity from the developers or of a decrease in desire for these titles from the fan base, but of hardware constraints. So then the dam broke. After a decade of quiescence in this hardware space, the fog lifted and we got 64-bit and multi-core and DX11, or newer. And with this newness of hardware and design came newness of appetites. So at 60 FPS, a frame is rendered every 16.67 milliseconds. Now, if that game is single core bound, then that means that all of the logic and physics and game simulation that is occurring on that main thread that has to be delivered every 16.67 milliseconds. So you're forcing the AI's entire decision-making process to occur within that very, very narrow time frame. And that is the reason that AI was dog shit in RTS titles for like 20 years. So, but with newer hardware, players said, okay, time to give us better AI. And so we got multi-core engines. And in order to serve that demand, Ashes required at least a quad-core CPU. And what players, again, newness of appetites, they said, give me a bigger world. And with multi-core AI, you can build a game of massive scale, because you don't have to tell the unit to back up or dodge or fire on target or whatever, because they can do that even if you're not watching them, because all of a sudden now you get these use of all these cores, and you don't and so that you don't have to cram all the decision making process, so that it competes with everything else going on in the game, so that it has to make these decisions within the span of a single rendered frame. Now it can go off and sort of kind of do what it wants across, and you can throw these threads across all the cores. So that's what a multi-core engine can do with AI. Now, what can it do with everything else? In older single thread bound engines, the entire game loop and all associated tasks run as one continuous sequence on one core. And so, like player handling, AI updates, rendering, and physics, they're executed in a serialized fashion, one after the other. And that means that the speed of the entire game is bottlenecked by the slowest task. Like if the physics calculations are too complex, then the rendering has to wait and your frames dip. But there's a benefit to that. There's a benefit to these single core engines, and that's just simplicity. You're not going to get race conditions because there's no need for all these complicated synchronization mechanisms. You can think of it like just everything dumps into the game thread, and that executes in a serialized fashion. And so when you're spreading things around on multiple cores, it can get kind of complex. But those multiple core engines execute things as opposed to serialized fashion in a parallel programming model. And so the game's workload is split into smaller independent tasks, and those tasks can be processed concurrently across multiple cores. And this task-based system would use, like, let's say there'll be a physics thread instead of how there used to be like a physics thread and an AI thread. Instead, it's going to take all that work and divide it into smaller tasks. And then it's going to put those tasks into a queue, and then the worker threads are going to pick up and execute the task as threads become available. So you remember when I was playing around with Raptor Lake and we modified the game file in Warzone to limit the renderer count to 7, and that matched the number of cores that we were limiting the game to. So instead of trying to spread all those workers around 32 threads, we limited it to 7 to help with cache residency, etc. So we've kind of discussed this in the channel. So but what can an RTS game, how can it utilize this multiple core and renderer worker counts and everything like that? Well, for instance, the AI for non-player characters can be calculated on one core, while the physics simulation runs on another, and you could put your rendering on a third core. And we talked about the limits of the game AI on these single thread engines, but multicore engines unlock the full potential of AI simulation. They can run on complex physics and use complex collision detection as well, in parallel with the main game logic and rendering. So this can allow for fully destructible environments. That was a huge thing to come out of this period. And more realistic ballistics. And all of this would be far, far too complex and too intensive to exist on a single core. But again, these engines are complex. How multiple threads access and share data is very, very different from single core engines, and that's going to require these complex synchronization primitives like semaphores and mutexes and all this type of stuff that I can let a real actual coder explain. But the point is that it adds overhead and complexity to the code, and there's a number of problems that come up for these devs they have to deal with these types of multi-core workloads, like race conditions being one of them, which just happens when two threads are trying to access the shared data and trying to change it at the same time, and this can lead to unexpected outcomes that might only happen once in 1,000 runs. So they're very, very difficult to pinpoint and correct. And there's also deadlocking, and this is when two or more threads are blocked, waiting for each other to release a resource, and the game will freeze. And so again, diagnosing why multiple threads stop moving requires specialized tools, and it's a very difficult process. And these engines are difficult to bug check. You can imagine why, because the exact order in which threads execute might not be predictable from one machine to another, one session to another, etc. So a bug might appear on one user's machine but not another's. And so again, keep this in mind for the testing. So we're dealing with also issues related to cache contention, where multiple cores are trying to access data within that same cache line. And these devs are also responsible for balancing load, so to ensure that no single core is underutilized and bottlenecking the scheduling. So the point is, they require significantly more engineering discipline than single core engines. The Nitrous Engine, developed by Oxide Games, of the which Ashes of the Singularity was the first to make use, was not just a multi-core engine, but it was packaged as a core neutral engine. So a standard multi-core engine would use dedicated threads and put the physics on one and the rendering on another, etc. A task-based approach would be a bit more granular, and it would assign tasks basically per core. So you'd have like animation on one core and render prep on another, or whatever. The Nitrous Engine parallelizes the work inside that task. So let's say you have 1,000 units in an RTS game. A task-based multi-core engine would say for all, like, have a loop, like for all 1,000 units, update AI. And what Nitrous would do would be like, on core 3, update units 1 through 99, and on core 4, update units 100 to 199, etc. So a task-based multi-core engine parallelizes at the task level. A core neutral engine parallelizes at the data level. And again, this is not my bailiwick. So if you're a coder and want to comment leave a comment that what I'm wrong about how I just described it, please do. I'm always looking to learn something. My objective here is to sort of cover what a core neutral engine is in a very high level way without getting too much in the weeds. So just like a high level understanding of what these guys were doing that was so different. So the idea of the core neutral engine was to minimize the bottlenecking that could happen within the main game thread by using a jobs-based approach that would break things up into much more granular data that could be spread more linearly across a greater amount of cores. What we did was probably not repeatable, says Chief Graphics Architect and co-founder of Oxide, Dan Baker. There are a lot of great games getting made, but there's also a lot of games that just weren't getting made, and they weren't getting made because people had either misgivings or misunderstandings of what a modern computer really could do. People were starting to ship 8-core CPUs, and the games weren't using them. There was an enormous amount of potential that was just there, and it was already shipping, people already had it, and their games really weren't using it. So to develop this engine at this time wasn't just bold. I mean, you could almost describe it as reckless. So in Wardell's own words, there was no DirectX 12 or Vulkan when we started working on it. We were building it based on the theory that such a graphics platform would have to be made, and got super lucky that they were made before the game shipped. So that's kind of funny to me. Now, a lot of the people who were involved in the development of this game and who worked with or for Oxide were also involved in the development of DX12, and were working with AMD on Mantle, etc. So a lot of these guys were involved in the development of these newer advanced APIs, but still, they couldn't have known that those would be released in time for the game's release. So when they were making the game, they couldn't have known that it would work. So it's pretty risky. I think we have to hat tip to these guys. If we're talking about DirectX 11, we're talking about immediate versus deferred contexts. The immediate context is the single game thread, the main thread that issues the draw call. Game threads can record work into deferred contexts, which are parallelized processes, but these are later merged into the immediate context. which serializes those parallel threads into a unified game thread for GPU submission. So the deferred context threads, they don't run wild, they funnel themselves into a single unified immediate context, which makes the draw call. In DirectX 12, on the other hand, there is no corollary to that immediate context. All work is recorded into command lists, which are basically the deferred contexts of DX11, only they submit directly to the GPU without the need to be collected into one serialized process. That serialization process is basically in DirectX 12 up to the developers. The API doesn't save them. They have to make it themselves. So developing a game in a multi-core engine gives all the control to and puts all the pressure on the developers, because it is they who must manage the synchronization and scheduling and submission to the GPU themselves. It's a fully parallelized process. If the threading model of the engine isn't properly developed, then threads are going to collide. Caches are going to thrash, and you're going to have synchronization stalls. So these devs accomplished this and beyond. They created a core neutral game engine that far surpassed anything of its time, and they did it without even knowing for certain whether an API that could actually run the game as it was meant to run would even hit the market in time for its release. Developing a game for DirectX 12 presents its own challenges. Game engines can parallelize culling, physics, animation, etc., but all of that parallel work eventually funnels into a single ordered submission stream to the GPU. In DirectX 11, the driver builds this serialized stream for you. API calls can be issued in any order, but the driver will validate, reorder, batch, correct, and submit to the GPU. The engine doesn't need to think about serialization. DirectX 11 begins this process during the API calls, not just at submission time. DirectX 11's enforced serialization offers advantages and disadvantages. It's stable and predictable. It offers automatic batching and state management. It is broadly compatible on older hardware. It just works. But it's doing a ton of work per draw call, which means lots of CPU overhead. When the scenes are complex and there are a lot of draw calls, DirectX 11 can suffer, and DirectX 11 cannot utilize async compute. By 2016, both AMD and NVIDIA GPUs featured multiple engines, a graphics engine, one or more compute engines, one or more copy DMA engines, which move data around efficiently without involving the CPU. DX11 can't run compute and graphics in parallel. It can't overlap copy with graphics. It's got one graphics queue and that's it, and everything is serialized. With async compute, if graphics are waiting on memory, compute can run. If compute is waiting on memory, graphics can run, etc. Async compute lets the GPU run compute tasks in parallel with graphics tasks, filling in the idle gaps. This increases total throughput. The developers of Nitrous utilize this highly parallelized jobs-based engine in combination with DirectX 12, a highly parallelized API. Within DirectX 12, they generated command lists from these jobs, feeding the graphics, compute, and copy queues within a custom synchronization model. Without the stability of DirectX 11 to fall back on, these developers had to build everything themselves. DirectX 12 doesn't build the command stream for you. The developers build it. They manage the ordering and synchronization. Only at the moment of submission does DirectX 12 enforce serialization, because that's what the GPU requires. Everything before that is the responsibility of the game engine. That is the responsibility of the developers. Nitrous was the first engine to truly utilize the parallelism of which GPUs were capable. So a quick note about the testing you're about to see. It's all at 1080p because initially this game was part of my test suite for the 9800 X3D. It was going to be in that video that I released a couple days ago. And then when I got into working with this game, I found the process so fascinating that I decided to dedicate it to its own video. But that's why all the testing is at 1080p, because that was a video about the 9800 X3D. So to isolate a CPU for testing, you test at 1080p. Theoretically, the problems that I encountered with this game could have been resolved by bumping pixel count and going up to 1440p or 4K, but I didn't do that. I stayed at 1080p because that's where I was testing at the time. So just keep that in mind, that if you're going to bump pixel count, that can resolve some issues that you might have with some bottlenecks that you see when you're trying to resolve these game problems. But if you force yourself to stay at 1080p, then you got to get creative. So I definitely had to get creative to get this game to run properly. Let's just take a moment here to appreciate this game and the developers who made it. The aforementioned Brad Wardell, CEO of Stardock, and the teams of Oxide and Stardock, including Dan Baker, Tim Kipp, Mark Meyer, Brian Wade, Nathan Heaslett, Steve Langmead, Michael Curran, Brian Clare, Chris Bray, Steve Egri, Ryan Murray, Tom Simmons, and I'm sure 100 other names I don't know. They set out to address the future of games and specifically the future of RTS titles. They advanced the development of multi-core engines by creating the first core-neutral engine, employing a job-based process for theoretically seamless scaling to 8 cores and well beyond. With all due respect to this group of pioneers, this is the point at which my story deviates from theirs. Because as much as I admire the ambition of Oxide and Stardock, as much as I respect the risks they took in building a core-neutral engine before DirectX 12 even existed, my time with Ashes of the Singularity showed me something sobering. On the most advanced hardware today, 9800 X3D, 5070 Ti, I couldn't simply let the game run as its creators intended. I had to strip it back from the parallelization these guys worked so hard to implement. As much as I respect these luminaries, my job isn't to develop game engines or APIs. My job is to make shit work. So let's get into this testing so I can show you how I did that. So if you wanted to know what a bottleneck looks like, here you go. If you've seen anything on this channel, you know that I don't pay much attention to average frame rate, and I only pay it any mind when I'm comparing it against the lows. I take the delta between those two and divide it by the average frame rate to produce delta as percentage of average frame rate. And that percentage represents smoothness of gameplay. I tested at 1080p because I was isolating the CPU for testing. 1080p low settings is not a realistic use case for the gamer who's bought these components. But part of my process in testing those components is to see how quickly we can arrive at a bottleneck. And a bottleneck is likely what you've got with a delta percentage this bad. I know that I'm the only one who uses this metric because I'm the one who invented it, but from all the testing I've done, the sweet spot is under 30%. That doesn't apply to every game. Some games are buttery smooth even at 45%, like Detroit Become Human, for example. But for the vast majority of games, if your delta as percentage of average FPS is above 30%, you're straddling that line of suboptimal performance. At 40%, it's very noticeable, and you will see microstutters. At 50% and above, it's unplayable. What saves this title is that it's an RTS, so you don't notice the poor performance as glaringly as you would in a single-player title. But still, if you're seeing numbers like this, you know you've got an issue. Now, we've discussed the Nitrous Engine and the concept of a core neutral engine, and we talked about multi-core engines and parallelization. But every engine, regardless of how sophisticated its use of multiple cores, has to reconcile something. Certain steps have to be serialized. The movements and targeting and pathfinding of the units the player deploys in an RTS game called unit micro, those can be parallel. Certain AI calculations can be parallel. Certain physics calculations, particle updates, audio mixing. But at the end of each frame, the game must produce a single authoritative world state, and it's that state that the renderer consumes to issue the draw call. If threads finish unevenly, the engine has to wait until all those jobs are reconciled before moving forward. With the Nitrous Engine, there is not a fixed main game thread in the traditional sense, but there's still a serialization point. That is the point where your FPS caps, and if the parallel jobs finish unevenly and the engine stalls waiting to merge them, that's where your 1% lows and deltas suffer. And the issue continues as you'd expect when we change game modes. Identical numbers, so we're stuck here. Changing from AI skirmish to 1v1 left our deltas no better off. And would you look at that? This game is so bottlenecked at 1080p that switching to the high preset did exactly nothing. Now, it's seemingly paradoxical that a big jump in the graphics preset could make frame rates go up, but it makes perfect sense with respect to a CPU bottleneck. If that bottleneck can be resolved with graphics settings alone, this is what you'll see. FPS jumps up dramatically because we're no longer CPU constrained. The GPU workload finally increased enough to mask that uneven reconciliation. The most graphically demanding preset finally succeeded where the others failed, in forcing the GPU to tell the CPU, I'm busy here, I'll get to you when I get to you. The thing is, was this really a CPU bottleneck? Well, no, it wasn't, and I realized this later when I saw the CPU utilization numbers. Once I saw those, I started to work off of a different theory. It wasn't a CPU bottleneck that I was observing. In fact, the 9800X3D was too fast for this game. Since its window of execution is so small, it led to timing events within the game engine. Since the GPU was idle at the low settings, that synchronization delay within the game engine didn't have anywhere to hide. What I was seeing here was not a CPU bottleneck, but a game engine bottleneck. And what's really interesting, though, is that my assumption of the CPU bottleneck didn't hurt me at all because I relieved it the same way, by ticking up the graphics settings. Increasing to the highest graphical preset finally achieved the critical difference in frame pacing behavior. I gave the GPU more work, and that internal timing weirdness that was producing bad 1% lows was masked. It wasn't a CPU bottleneck, but I remedied it in the same way that I would remedy a CPU bottleneck. As you can see from the note here, I also dealt with freezes in the crazy preset. Since I'd been running the game all day at this point, we can safely rule out hardware and thermal concerns. The low and high presets barely touched the GPU. The crazy preset finally gave the GPU heavy compute, heavy shading, heavy copy and streaming, and a lot more command lists. It's the first time the GPU was busy. Nitrous was built to run lighting, occlusion, simulation, culling on compute and to overlap that with graphics. At the low and high presets, most of this was underutilized, but at the crazy preset, it all woke up. More saturation of the graphics queue, multiple compute queues active. When async compute is active, the engine must explicitly manage barriers and fences. These are synchronization primitives that control resource transitions. A barrier prevents the GPU from reading a texture before it's finished being written, or prevents compute from writing to a buffer while graphics is still reading it. And think of the fence as sitting between the CPU and the GPU. It controls when work is allowed to proceed across queues or CPU-GPU boundaries. If either of these is too conservative, too aggressive, poorly timed, or mismatched, you get freezes, not crashes, freezes, because the GPU is waiting for a fence that never arrives. The 9800X3D exacerbates this because it's too damn fast. Jobs complete earlier and command lists close sooner than expected. It's too fast for the engine's timing assumptions. So you see that 36.51% delta right there? Well, we've resolved the game engine bottleneck. It's a damn sight better than 50%, but it's still not good enough. If I see that percentage above 30 in almost any game, I know there's still work to do. So let's get back to that. First, let's demonstrate the resolution of our bottleneck with some hard data. So as I mentioned before I looked at this data, I was still thinking that the bottleneck was at the CPU, but if the CPU is working so hard, why is its utilization so low? 15% in the low presets. Theoretically, it's still possible to have a CPU bottleneck with low utilization, but that would typically involve one maxed out core and all the others sitting at idle, which is not what I saw. Here, at the low preset, with CPU utilization around 15% and GPU utilization around 25%, the engine is doing just enough work to hit 180 FPS, but the frame time floor is very low. We were getting 80 in the 1% here. The engine didn't have enough work to keep its own scheduling stable. Nitrous was designed to run thousands of micro jobs across multiple cores. With such low utilization, the pipeline is underfed, and the graphics, compute, and copy queues are starved. So the GPU drains its queues, goes idle, waits for the CPU, waits for barriers and fences, and all this waiting produces microstalls, which manifest in poor lows. DirectX 11 does a lot of this kind of work without the engine even knowing it. It stretches or compresses GPU work to keep queues full. But these runs were all on DirectX 12, which leaves everything up to the developers. It does not hide timing mismatches or queue underutilization. It doesn't reorder work or insert barriers. DirectX 11 hides the engine's flaws. DirectX 12 exposes them. So I got some crashes in this game. They happened on the high preset, which was the preset I ended up using on most of this testing. Several of those runs were not recorded. Some made use of affinity pinning, some didn't. The late game crashes happened only on the high preset and only on DX11. In DX12, the game ran poorly, so I moved on from it. But the problem there was never late game crashes, or crashing at all. I think DirectX 12 handled the parallelization and core neutrality of the game engine better than DirectX 11 did, which is to be expected, but the deltas were very poor. In DirectX 11, the game crashed, but the deltas were better, leading to a better gameplay experience when I did finally find the right core affinities. Despite DirectX 12 being optimal for multi-core use, I can only conclude that the game engine has yet to be optimized for the hardware I'm running. DirectX 11 makes far less efficient use of multi-core and certainly of core neutral game engines that were designed to spread parallelization out across multiple cores, but with some tweaking, this game in its current state runs better in AM5 on DirectX 11. And here we run into a fundamental limitation of parallel computing known as Amdahl's law. A game cannot be 100% parallelizable. Too many parts of the process, like the synchronization of threads, will remain serialized. You can speed up the task, but Amdahl's law says that the serialized portion of that task will always remain the bottleneck as you scale the parallelized portion out across a greater number of cores. Take a task that is, say, 95% parallelizable, as represented here by the green line. The math is pretty simple. Let that one task be represented by the number 1, then divide 1 by the serialized portion of the process, which is 5%. 1 divided by 5% equals 20. That 95% parallelizable process can, in theory, become 20 times faster. Across how many cores will it have to scale for that process to become 20 times faster? Well, it'll happen when the sun sets in the east. In other words, it scales logarithmically for an infinite number of processors. But the point at which returns diminish to almost nothing is determined by how serialized the task remains. That's Amdahl's law. So what did we do here? Well, we implemented Amdahl's law, didn't we? We took a game that was designed with parallelization in mind, with a then brand new highly parallelized API in mind, DirectX 12, and we introduced greater serialization into the process by running it in DirectX 11. DirectX 12 does away with the single unified game thread. It leaves the final synchronization up to the developers. In DirectX 11, that step is handled by the driver. The engine is designed to scale across higher core counts. What does Amdahl's law teach us? That the serialized portion of every task becomes the bottleneck in that scaling. What happens when you run this game in DirectX 11? You increase the portion of the game's tasks that are serialized. You limit its scaling. Combine that with a 4-core affinity, as we've done here, and you get a crash. Amdahl would be proud of this crash, but we improve the deltas, and that is the development of consequence. So we march on in DirectX 11. Given the nature of Nitrous and everything we've discussed about parallelization and multi-core engines, it's hardly surprising that the game crashed with hyperthreading off. What's interesting here is the dramatic reduction in the delta percentage. Hyperthreading introduces a logical core that becomes a sibling to its physical core, but these two cores, physical and logical, share the same resources, the same L1 and L2 cache. So when we cut off the competition for those resources, it helps with stalls and timing variance and leads to better 1% lows. But the game expects sibling cores. Remember that this is a jobs-based engine. It works by splitting up tasks into smaller jobs. While latency-sensitive tasks like game reconciliation prefer the full physical core, the engine can offload smaller tasks to the sibling cores. The engine has assumptions about thread concurrency that you break by disabling hyperthreading. So when we further constrain the engine by limiting core count from 8 now down to 6, it won't even load a match. Now, I knew that the game would crash with hyperthreading off, but these are still pretty interesting results. The interesting part was when they crashed. On 8 cores with no hyperthreading, the game crashed right at the end of the match when you've got tons of units on the map. The CPU preparation is stalled, the GPU has to wait, and this triggers a TDR delay. I went into the registry to tick up the TDR delay for the GPU, but to no avail. We've tried hyperthreading on with 8 cores. That didn't work in DirectX 11 because of Amdahl's law. We tried hyperthreading off with 8 cores, which crashed late, and with 6 cores, which crashed early. But we learned that we can improve deltas by tightening that core count in DirectX 11. At this point, we are narrowing down our options, and that's a pretty good place to be when you're troubleshooting, because you know that a solution is coming. So what's left to try? Well, let's move it back now to 6 cores, 2 through 7. So we remove Windows scheduler interference from core 0 and 1, which is the default landing zone for background tasks. Let's turn hyperthreading back on and see if we can't balance Amdahl's law with the engine's thread concurrency assumptions. And when you see me employing emojis, that's a happy Dave. What makes for a happy Dave? Deltas under 30% makes for a happy Dave. Take my word for it, this is where you want your Dave. Tons of frames, great lows, buttery, smooth, gliding across the map, zooming in and out. Even in an RTS title, you do feel the difference. That's where you want to get to, folks. This is what it's all about. So why I wanted to make this video, I think it's a great example of like when worlds collide. You have this great, fascinating Nitrous Engine that was revolutionary for 10 years ago. And here I am trying to make this old game run on newer hardware. And sometimes those old assumptions with the hardware of the day don't match up to today's hardware. And you have to fit a square peg in a round hole to make the game work on newer hardware and platforms. And I thought that this was a fascinating example of that. I also thought it was a great example of actual irony. It's truly ironic. So let's review for a second. So 10 years after the release of Ashes of the Singularity, running on the most advanced hardware in the consumer space, 9800X3D, 5070 Ti, I had to butcher this game to make it work. And that's why I wanted to pay homage to these developers. I wanted to pay them their due before I took a dump on their legacy. I mean, I made it work. That is the goal. I mean, I'm not a coder, not a game dev. I'm just a guy who makes things work. And that's what I did. And so, goal achieved, but this engine is a monumental achievement. When the last great RAM crisis happened, other gaming genres were able to take off, but doing more with less was not an option for the studios that produced RTS games for reasons we've covered. And when that better hardware became more widely available, these guys pounced. I mean, this effort was really a prodigious one. It brought about an RTS revival. It set a performance standard for strategy games. And many of these developers were developing DX12 at the time. So this game was also a flagship for a brand new API. They introduced asynchronous compute to leverage the resources of the GPU in ways that had never been imagined. I mean, the list goes on and on, but all that happened on 8 cores with DirectX 12. I mean, that's what they designed it for. And to get the game to work 10 years later on infinitely more powerful hardware, I had to pin it to 6 cores on DirectX 11. I mean, now that's irony. Not like the Alanis Morissette song, you know, where she made the song about irony and there wasn't one fucking example of irony in the song. No, this is real irony. So I really wanted to pay homage to these developers after I realized just how much I had butchered their legacy. You know, I remember reading Thomas Hardy's Test of the D'Urbervilles, and as soon as I finished that book, I immediately felt bad for any non-English speaker who read it in a different language. You know, I didn't get to experience the author's intent here, and I sort of felt like I didn't get to experience the author's intent when I got the game to work, but I got to experience it a bit when I researched the game and when I dove down this rabbit hole. So this was a very rewarding experience for me. So I hope you think about the developers of the Nitrous Engine the next time you play a modern RTS title. You owe them. We all do. And I hope you've enjoyed diving down this rabbit hole with me. We've got some advanced RAM tuning coming up for the 9800X3D. I'm going to test the 5070 Ti. If you are interested in that content, and if you agree that the real bottleneck is you alone are responsible for fixing your shit, then this is a place for you. Please like and subscribe, and I'll see you in the next one.